Good morning, everybody, and welcome to our second session together as we're thinking about In Search for Certainty. Last night we were thinking about all that God has revealed to man that is calling man back to his Creator. Science can only verify what is of nature, natural order. It can't verify or disprove God's existence because God, by definition, is supernatural. But the point last night is God has given us a lot of himself. Even though we can't verify God by science, we can identify information that he's given to us that's outside of natural order. And if we see these things consistently and they're statistically improbable, then we should start considering an influence beyond just nature. And last night we saw that the atheist and the agnostic closes their mind to that kind of information. So our week together, we're examining information that God's given us, statistically improbable, which should cause us to consider him. And of course, we can't understand him without his help. And so in this session, if you like science, you're really going to enjoy this session. It took a while to get it put together. It's entitled The Uniqueness of the Earth. And what I want to show you is that the planet that we live on is extremely unique. It's extremely unlikely to occur by natural chance, which then beckons us to the fact that there must be a creator, there must be a designer to create such a specialized planet for the one who reflects his image to be the central creature on that planet. So let's look at this, the uniqueness of the Earth. I'm going to be sharing with you 15 reasons that the Earth is unique. About 500 years ago, there was an astronomer, Nicholas Copernicus, that proved the Earth rotated on its axis. We'll talk more about that later, with the other planets in the solar system revolving around the sun. And what motivated Copernicus in his studies was to understand the mechanism of the universe brought to us by a supremely good and ordered creator. As he looked out with his telescope and saw the intricate design among the planets and the stars, he knew that there was a good God who was behind the design of it. Design demands a designer. Well, I don't know if you've ever thought about this before, but just how unique is planet Earth? Is there a lot of other planets in our galaxy, the Milky Way, that would inhabit life, that would be similar to the Earth? I grew up watching Star Trek, Lost in Space, and later Star Wars. A lot of these science fiction series present the idea that we can just beam in or hop on our spaceships and go to other planets and go down and enjoy a picnic lunch and then beam back up and go somewhere else. Well, is that really the truth? Is that realistic? And what we're going to see today is no, it's extremely unlikely. There is something extremely unique about the Earth and life on it. From an observational standpoint, none of the dozens of planets and moons in our solar system have an environment which can sustain complex life. Furthermore, we've already found hundreds of planets orbiting neighboring stars. Almost all of these are gas giants, similar to Jupiter. Again, not able to inhabit complex life, support complex life. Humanism, that science in which man is a sinner, has sought to discredit the existence of a creator by opting for the philosophical principles such as the principle of mediocrity. And this principle, which is very anti-God, states that the Earth occupies no preferred place in the universe. Man's status and location are mediocre. They are unexceptional. Man has no privileged position in the universe. Well, that's contrary to what our Bibles tell us. Genesis 1, God created this planet. It relates to man. Man was put on it to rule over it. Man was created in God's image. He's to represent God's authority on the planet. So we have a stage that God has set in order to act out his plan of redemption and restore this creature that he wants to have fellowship with. On the grand cosmic stage, planet Earth is really the center of God's attention. And so it stands in contradiction to the principle of mediocrity. So, does science verify that there truly is nothing spectacular about the Earth? Well, let's just look at some of the evidence. First of all, we have the abundance of liquid water. There's large amounts of liquid water on planet Earth. That's necessary to sustain an inhabitable planet with carbon-based life forms. Liquid water is the basis of all vital chemical and physical activities on which life depends. And most organisms are made up of at least 50% water, and our human bodies are made up of about 70% water. Another key thing that's unique on the Earth is where it is in the galactic inhabitable zone. So if planet Earth was further out from the center of the Milky Way, the black hole that everything circulates around within the Milky Way, we wouldn't have the heavy metals necessary to support complex life. But if we were closer to the center, we would have strong gravitational pull. We would be bombarded with all kinds of X-rays and gamma rays, particle radiation, and that would destroy life. So the Earth can't be too far away from the center, or it wouldn't have the heavy metals to support life. And if it's too close to the middle, gravitational pulls, X-rays, radiation, so forth would eradicate life. But then there's another component, and that is the galaxy's spiral arms. If we were a planet located within the spiral arms, there would be these constant stellar collisions, supernovas. There would be a constant threat of destruction, which means life couldn't develop, naturally speaking. I'm taking a naturalist point of view here. So let me just show you a picture. Our planet is right here. This is a cross-section of the Milky Way. Here's the center. You can see the spiral arms here. These are heavy clusters of stars and planets, lots of collisions. So we're not too far away that we don't get the heavy metals, and we're not too close that we don't get bombarded by radiation. Just happen to be in this nice little spot in which life can be sustained. And then we also orbit a main sequence G2 star, sometimes referred to as a yellow dwarf star. It's actually small compared to most stars. And orbiting a smaller star would require a planet to have a much closer orbit to maintain an habitable zone of liquid water. However, the gravitational pull of a star would be much greater and cause the planet's rotation to synchronize with the orbital rotation of the sun. So we're going to see that if we were orbiting a big star, that's not going to work. A little star is not going to work, because if we were orbiting a smaller star, what we observe of the planet Mercury would be what happened. Mercury doesn't rotate on its axis. It faces the sun in one place all the time, so it just gets cooked. Orbit around a yellow dwarf star that's big enough to keep that from happening, but not too big, that would radiate us with all kinds of radiation and also keep us at the right temperature. Actually, this is a graph of the stars in the Milky Way, in the galaxy that we live in. So this axis is how often these stars occur in space. And you can see the far majority of stars here are red dwarfs. This axis is magnitude, the brilliance of the sun. And this axis has to do with spectral type of the star, O being the hottest surface temperature, and then the stars cool down as you go to M. Red dwarfs are generally thought to be stars that are burning out. White dwarfs would be the brightest, hottest stars. And here we are. We just happen to be around this G-type yellow dwarf star which has a magnitude of about 4.83. It's estimated to be brighter than about 85% of the stars in our Milky Way galaxy, which again are mostly red dwarfs. The red dwarfs don't have enough light, the right spectrum of light, to sustain complex life. White dwarfs would be too hot. We just happen to be orbiting around a G-type star that's the right size to keep the planet from locking in, so it's always facing the star, and it's also the type to not radiate us with too much radiation or be too, like the red dwarf stars, not having enough light to emit in order to sustain complex life. Number 4, large gas planets are in our solar system, and that's needful in order to have a planet to maintain complex life. These larger planets, gas planets like Jupiter and Saturn, Neptune, they're like a big magnet to these comets. And so as comets circulate into the solar system, they will absorb them and keep them from colliding with the planets closer into the sun. About 30 years ago, I remember watching, it was like when the internet was first getting going, and I remember watching a comet collide with Jupiter. It broke up in about 4 pieces, and you could see the collision on the planet through the telescopes. And so these gas giants are necessary to absorb these comets that come into our solar system to keep us safe. In our solar system, it's estimated about 200,000 asteroids, but only a few dozen orbit within the Earth's proximity to the sun. But there are about 400 comets that make infrequent visits into our solar systems, and 50 of those make excursions within Earth's proximity to the sun. Actually, there's one just heading by the Earth towards Venus right now, and that's one of the 50 comets that make kind of a close excursion. But overall, these large gas giants protect us from comet collision. Then we have this stellar and habitable zone. If the Earth was 5% closer to the sun, the Earth's oceans would boil. That would create a greenhouse effect, which is what we see happening with Venus, and create temperatures on the surface of about 900 degrees F. Obviously, nothing's going to grow in that. Life can't be supported by those kind of temperatures. But if the Earth were just 10% further away from the sun, the oceans would freeze. We need the abundance of water to sustain complex life. So there's really this narrow range which a planet can be from the sun in order to keep the oceans from boiling, have a greenhouse effect, which would destroy all life, or for the planet to be too far away to where the water freezes and wouldn't support complex life. We also have a nearly circular orbit. That's important because if we had an elliptical orbit lasting for months, we would experience extreme temperatures on the Earth. And again, that would wipe out all life on the planet. But we have nearly a circular orbit, so the variations that we get in radiation from the sun don't vary that much through the year. We also have an oxygen-rich atmosphere. The Earth's atmosphere is mainly 2 gases, 78% nitrogen and 21% oxygen. And oxygen is an element that almost all life must have. Ozone is a form of oxygen that provides this screen over our atmosphere. It shields the Earth from harmful radiation, such as ultraviolet bandwidth light. So oxygen is critical to supporting complex life. Then we have this atmospheric transparency and shielding. The nitrogen and oxygen mixture in the atmosphere actually shields cosmic radiation from coming in. It only allows the light which is necessary, visible light, in a very small spectrum to make it through and support complex life. What's harmful is kept out. What's needed to support life is allowed to come in. If further from the sun, the Earth's atmosphere would need more carbon to create a greenhouse effect to keep the planet warm enough to sustain life. But too much carbon shields the visible light from coming in and then would diminish the opportunity of plants to create photosynthesis. So again, the content of our atmosphere is specifically designed to allow the right light to come through, and it shields us from the radiation that would destroy life. We also live on a planet of correct mass. A smaller planet would not generate enough surface gravity to keep the atmosphere in place. It would just dissipate in space. Again, we see that on Mars, we see that on Mercury. If the Earth was greater in size, the increased gravitational pull would force more gases like water, methane, carbon dioxide into the atmosphere. So stronger surface gravity would reduce the rate in which these dissipate in space, but they would also create more gas and create a greenhouse effect over the planet. A bigger Earth would exist as a gas giant. This is what we see in the planets in the outer ring, like Jupiter and Saturn, Neptune. And that makes it impossible then to have complex life. This is a picture just to give you a perspective. This is the sun, and this is our planet Earth in comparison to the sun. And you can see how much bigger these gas giants, Jupiter and Saturn, Neptune, Uranus are. Number 10, orbit a large moon. And this is really critical for sustaining complex life. In respect to the rest of the solar system, the size of the moon is quite large in comparison to the size of the Earth planets. We don't see this combination anywhere else. So what does this accomplish? A large moon stabilizes the axial rotation of the Earth at 23.5 degrees. So our Earth is tilted on its axis about like this and rotates this direction, and then it rotates around the sun. So the large moon stabilizes that axial rotation. That ensures temporal seasoning changes worldwide. Also, we get this tilting back and forth on its axis. And so rather than getting a small band around our planet that can grow vegetation and have life, because the planet is constantly tilting back and forth, one revolution around the sun each year, we get a widespread inhabitable zone on the planet. Yeah, the snow flies in the wintertime, but a few months later it warms up and we have vegetation. That provides an opportunity for life to occur on the majority of the planet. Also, the size of the moon causes significant tidal mixing. This keeps the oceans, their water masses from getting too cold and warm. It's constantly stirring them up, and it prevents thermal stagnation of the various bodies of water. It also is constantly turning up life-supporting elements from the strata in the ocean that are needed for supporting life. So the moon is like a big spoon. It stirs the oceans, keeps them from stagnating, keeps the minerals and all the elements needed for complex life in circulation. We also have a magnetic field circulating the Earth from pole to pole, and it's strong enough to prevent solar winds from stripping away the atmosphere. It's literally like a big shield around the Earth. And some of the planets don't have that, and they don't have atmospheres. We also have a moderate rotation that keeps days from getting too hot or too cold. If, for example, our rotation was a lot slower than 24 hours in a day, approximately 24 hours in a day, then we would have these wide variations that get very hot during the day, very cold at night, and again, it wouldn't be a habitable zone to support complex life. We also have plate tectonics. Various plates on the Earth's crust, they're in motion, and what's interesting is the thickness of these plates. Some 40 to 30 miles, is thick enough to prevent the Earth's molten core from cooling off too fast, but they're thin enough to move, which allows for this constant circulation of carbon and other elements essential to support life. The surface of the Earth seems to be optimized by the number of plates and the ratio of liquid water to continents to maintain this dynamic that we have with plate tectonics on our planet. We also live on a planet that doesn't support one portion of life, but it has a wide variety of biomechanisms to support a variety of different kinds of life, from the smallest bacteria into larger animals, from all kinds of different vegetation. Mechanisms on our planet have been designed with this broad spectrum of supporting life. Another key thing is not only are we orbiting a G2 yellow dwarf star that just is the right size and brilliance, but it's a stable star. Its output only varies 0.1% over a full sunspot cycle, which is about 11 years. Among sun-like stars, a wider variation of light intensity has been observed, and obviously that would cook any kind of life on the planet if you started getting high amounts of radiation. We need a consistent star in order to prevent climate swings on the Earth, which would destroy life. So those are just 15 components. If we just take those 15 components, researchers have calculated the probability of other planets randomly possessing, again, these 15 critical parameters needed to support complex life would be about one planet out of every 10 to the 15 planets. All right, so that's what this number looks like. One with 15 zeros after it. Just those 15 parameters, how likely is it, naturally speaking, that a planet would have those 15 characteristics to support complex life? One in every 10 and to the 15th planets would. Well, it's thought that there's about 200 billion stars in the Milky Way galaxy, and that's to say, for discussion purposes, that each of these stars had 10 orbiting planets. What would be the likelihood then, out of these 200 billion stars with 10 planets, that we would get a planet like Earth just considering these 15 characteristics? Well, probability-wise says that we shouldn't find a planet like this except once in every 500 Milky Way type galaxies. And so we live actually in a very large galaxy, and given these 15 parameters, we should only see a planet like Earth in about 1 in 500 galaxies. Again, the planet that we live on is very unique. Hugh Ross, in his book, Big Bang Refined by Fire, he actually addresses 75 key necessary elements, physical parameters to sustain complex life. And he takes the probability of a planet having all 75 of these, which the Earth does, and his analysis concludes that there should not be any planets in the whole universe capable of supporting life as a result, naturally speaking, from the Big Bang. We live on a planet that is very uniquely designed to support life, a particular kind of life. And to see these same parameters naturally occurring is astronomically improbable. That calls our attention to a designer. It's interesting that some of these science magazines, some of the writers are acknowledging this. Jay Glantz in Science Magazine writes, "This type of universe, however, seems to require a degree of fine-tuning of initial conditions that is apparent conflict with common wisdom." In other words, he say it's so astronomically impossible that all these parameters would occur by chance that there has to be some fine-tuning in order for it to happen. C.W. Hawking in Astrophysical Journal writes, "In all these worlds statistically miraculous events would be necessary to assemble and preserve the fragile nuclei that would ordinarily be destroyed by higher temperatures." There's something miraculous, there's something needed beyond nature in order to preserve life. The conclusion is the Earth is an extremely unique planet. Another thing that's a calling card of the Lord, how he wants us to understand the uniqueness of the Earth, is the convergence factor of the sun and the moon during a perfect solar eclipse. When we have a solar eclipse, so let's say that we have the moon here, it's blocking the sun's light from the Earth. Well, what's interesting is that when we have a perfect solar eclipse, the Earth's diameter its distance is exactly what's needed to block out the sun, but leave the coronosphere of the sun visible. So we get to see the outer ring of the sun. We don't get to see that all the rest of the time. And during perfect solar eclipses, we get to see stars that we don't normally get to see because of the sun's brilliant radiation and light blocks it out. And so, for example, we see stars that we believe are here, but are actually here. And so this proved Einstein's theory of relativity, that the light of this star is bent by the sun's gravitation and actually follows this course. And so we know from observation where the stars are located, but their appearance is different when there's a perfect solar eclipse. So it's really fascinating. The only planet in the solar system that has this dynamic in which we get perfect solar eclipse. The diameter of the Earth, the diameter of the moon, the distance from the moon to the Earth is exactly perfect, so we can see the coronosphere of the sun. The other thing that does is it provides us the opportunity through spectral analysis to see the elements that are in the periodic table. And so that's another benefit of these full solar eclipses. Spectral analysis of the coronosphere of the sun verifies elements within the periodic table. Now, another thing that's really, I think, fascinating is that not only is the Earth an extremely unique planet for supporting life, but it also has orientation to present the unique opportunity for man to understand Earth's uniqueness. What we see in visible light is a very narrow slice of spectrum in the electromagnetic range, and only one part in 10 to the 25th. In other words, that's all we see of the whole electromagnetic spectrum. But the light that's permitted for us to be seen from the sun during these full solar eclipses, again, is something that we can view. The distances, the diameters, the amount of light we can see, all of this is so improbable. It has to be by design. So, doesn't the Earth's uniqueness suggest a unique purpose and design? Otherwise, there would be many other planets like our own. Albert Einstein, perhaps one of the wisest men that's ever walked this planet, said this: "Everyone who is seriously interested in the pursuit of science becomes convinced that a spirit is manifest in the laws of the universe, a spirit vastly superior to man, and one in the face of which our modest powers must feel humble." So, in conclusion, the Earth is not only an extremely unique planet for supporting complex life, but has been exceptionally oriented to provide Earthlings the opportunity to understand its rareness and design. So let's consider these unique properties. There is only one creature, man, on the planet with the cognitive capability of understanding Earth's uniqueness to do so. The sun and moon's shape, size, distance from the Earth produce perfect solar eclipses. So we can verify things that we wouldn't normally be able to see. No other planet is known to have this. And the sun's spectral density, information during perfect solar eclipses, is precise chemical element information, is very narrow frequency range of electromagnetic. The narrow frequency band corresponds to actual electromagnetic frequency range that man can see. And number 5, the natural frequency band is not filtered out by the Earth's atmosphere, as is nearly all the other electromagnetic spectrum. The sun's size, sequence, and intensity are optimal for gaining absorption data. And number 7, stars on the opposite side of the sun are positioned in such a way that during perfect solar eclipses, Einstein's theory of relativity was demonstrated to be accurate. All right, so we'll stop there and open it up for any questions. I find when we start looking at the uniqueness of our planet, it's just fascinating to realize how intricately we are designed, our planet's designed, our solar system is designed. God has set the stage to act out his plan of redemption. And as we grow in our understanding and have the tools to investigate these things, we just stand back in awe because the detail just gets greater and greater that there is a designer who has put our planet in place and put us upon it.